Okay, guys, we are back at it. Got something a little bit different than yesterday. Got a different Radican, and obviously notice that our radical is down in the denominator rather than being in the numerator. But we can still do this guy using trigonometric substitution. Okay, so I take a look at what we have, and I have this constant plus x squared in the Radican, and I know it's going to have to be like a squared plus x squared. Okay, so I know I'm going to have to consider this, whether I do it on paper or do it in my head. I have to consider this guy as being 3 squared plus x squared dx. Okay, and then we go to our paper, and we say, okay, well, what should I use here? Okay, so it looks like we're in this situation right here. So I've got to do x equals a tangent of theta, where a is 3. Okay, so I have to do my x equals a tangent of theta, where a is 3, so it'd be x equals 3 tangent of theta. Okay, so let's see, then our dx, well, 3 is a constant multiplier. Derivative of tangent is secant squared theta d theta. Okay, so let's see what happens here. Okay, I've got the integral 1 over square root of, let's see, that would be 3 squared plus 3 tangent theta squared, and then we're going to multiply that by 3 secant squared theta d theta. Okay. All right, so let's see. Notice down here in the Radican, I have a common factor of 3 squared. So I'm going to pull that guy away. Okay, so I've got that 3 squared. And then let's see, I will be left with 1 plus tangent squared theta. Okay, and then I still have this 3 secant squared theta d theta. Okay, so if we go to our Pythagorean identities, because I'm looking at that 1 plus tangent squared, okay, and 1 plus tangent squared is secant squared. So I can substitute in secant squared right here. Okay. So let's see, we get 1 over square root of, that would be 3 squared secant squared theta, and then I have my 3 secant squared theta d theta. Okay, so notice that my Radican is a perfect square, so if I take the square root of that, I'm going to get 3 secant of theta, and then up here I've got 3 secant squared theta d theta. So obviously the 3's are going to cancel, and then one factor of secant will cancel here with one of them up there, and so I'm left with a factor of secant theta d theta. Okay, so let's see, we go to our sheet right here, and we can integrate that. Okay, the integral of secant x dx, or secant theta d theta, would be the natural log of secant of theta plus tangent of theta plus our constant of integration. So let's see, we get the natural log of the absolute value of secant of theta plus tangent of theta plus c. Okay. So now, really, just like the previous problems we've done, it comes down to how do we get rid of that theta and get it back in terms of x. Okay, so let's see. Well, if I go back up here, tangent of theta, tangent of theta. Okay, so wouldn't this guy just take us x over 3 is equal to tangent of theta? Okay, so I've got something to put in for tangent of theta. Okay, so that's good. So now I need something to put in for secant of theta. Okay, so let's see. So if we go back to, again, our Pythagorean identities, and I'm thinking, okay, well, secant of theta, that would be the square root of tangent squared plus 1. Okay, so let's see. So if I use that, secant theta equals the square root of tangent squared theta plus 1. Okay, so I think we're in good shape here. All right, so let's see. Natural log of the absolute value. Secant theta is right here. Square root of tangent squared theta plus 1 plus tangent of theta is x over 3 plus c. Okay, well, we know tangent of theta is x over 3, so why not put x over 3 in here? So we'd have tangent squared of theta would be x over 3 squared. So we get the natural log of the absolute value of the square root of, okay, that would be x over 3 squared plus 1, and then I have this plus x over 3 outside. Okay, all right, well, we're in good shape because we've gotten rid of all of our thetas. Now it's just a matter of just simplifying this. Okay, so let's see what happens here. Natural log of the absolute value. Okay, let's see, this square root. Well, that would be x squared over 9. That would be 9 over 9. So it looks like I'm going to get x squared plus 9 all over 9 plus this x over 3 plus a constant of integration. Now notice this denominator in the radicand is a perfect square, so I can take the square root of that. Okay, so this gives me the natural log of the absolute value of the square root of x squared plus 9 all over 3 plus x over 3 plus a constant of integration. Now notice that I have a common factor of 1/3 here that I can pull away. Okay, and I like this guy because when I pull him away, okay, I can use a property of logarithms. Okay, I'd be left with square root of x squared plus 9 plus x plus this c. And notice I have the natural log of a product, so I can use the product rule. That would be the natural log of the first factor, 1/3, plus the natural log of the second factor, which would be the absolute value of this guy right here. X squared plus 9 plus x plus c. All right, now, some people would say that this is an appropriate answer, and I would agree with them, okay? There's nothing wrong with that answer, okay? But other people would say we could simplify this even more. Okay, here's the reason. This is a constant, and this is a constant. So obviously, natural log of 1/3 and whatever this constant are similar terms. Okay, we just don't know what that constant is, but we know we can add constants. Okay, so you will see a lot of times, you'll see this answer written as the natural log of the absolute value of the square root of x squared plus 9 plus x plus some constant of integration. Now here's the cool thing. We have no idea what that constant of integration is. So you can let it be anything whatsoever. So you could still let that constant of integration be c. We just know that this c is what we get when we add that c and that natural log of 1/3. Now, if you want to change that to something else, a k or a p or whatever, by all means, go ahead. We've talked about that already. But a lot of publications, i.e. textbooks, okay, would say that is the correct answer, and this really, although it's correct, it's not as simple as this guy. Okay, I would take either one though. Okay, all right, like that guy. That's pretty cool. Let's try another one like that. Okay. All right, so let's see. Okay, same type of situation. Let's see, we have 1 over square root of x squared plus 4 squared dx. Once again, we are in the same situation right here. It's just rather than having a squared plus x squared, they have x squared plus a squared. Same situation, doesn't make any difference. So we have to use a, which is 4, times tangent of theta. Okay, so x is going to be a, which is 4, times the tangent of theta. Okay, so when I take the derivative, dx, 4 is a constant multiplier. The derivative tangent of theta is secant squared theta d theta. Okay. All right, so let's see what we got. We got to go back and we got to substitute here. Okay, so I get 1 over the square root of, let's see, that would be 4 tangent theta squared plus 4 squared times our dx is 4 secant squared theta d theta. Okay, let's see, down in that denominator, I certainly have a common factor of 4 squared. Okay, so let's see, we pull out the 4 squared and I'll be left with tangent squared theta plus 1. Okay, and then I still have this 4 secant squared theta d theta. Okay, going to our Pythagorean identities, we know tangent squared plus 1 is secant squared, so we substitute that in there. 1 over square root of, that would be 4 squared times secant squared theta, and then we still have that 4 secant squared theta d theta. Okay, well, now we have condensed this radicand down to something that's a perfect square, so we can take the square root of it. Okay, so the square root of that radicand would be 4 secant of theta times 4 secant squared theta d theta. Okay, so now we can cancel off the 4's and we can cancel off 1 factor of secant. So we end up with the integral of secant theta d theta. Okay, and once again, we go here and we can integrate that. Okay, so we get the natural log of the absolute value of secant theta plus tangent theta plus c. Okay, so we have done our integration, so now it's just a matter of getting rid of the theta and getting it back in terms of x. So let's attack it the same way we attacked the last one. Okay, so let's see. We know we can take this guy, and if I divide both sides by 4, I'm going to get x over 4 equals tangent of theta. Okay, so that takes care of this. Now I need something here. Okay, so let's see. We know that secant squared theta equals tangent squared theta plus 1. So the secant of theta equals the square root of tangent squared theta plus 1. Okay, so we have something to work with. Okay, so let's see, natural log of the absolute value. Okay, that would be the square root of secant theta is square root of tangent squared plus 1. So we'd have tangent squared theta plus 1 plus tangent of theta is x over 4 plus our constant of integration. Okay, so we know tangent is x over 4, so we can put x over 4 in here as well. All right, so we get the natural log of the absolute value of the square root of See, that would be x over 4 squared plus 1 plus our x over 4 plus our constant of integration. Okay, just keep moving forward. All right, so let's see, this would be x squared over 16. That'd be 16 over 16. So we get the square root of x squared plus 16 all over 16 plus that x over 4 plus our constant of integration. And of course, we can take the square root of that denominator there. Okay, so I get the natural log of the absolute value of the square root of x squared plus 16 all over 4 plus x over 4 plus our constant of integration. And of course, we've got a common factor of 1/4 that I can pull out. All right, so we'd have the absolute value of 1/4 times the quantity of the square root of x squared plus 16 plus, that would just be an x now, plus c. Okay, so again, we have the natural log of a product of two factors, so we can use the product rule. And so that would give us the natural log of 1/4 plus the natural log of the absolute value of the square root of x squared plus 16 plus x plus a constant of integration. And once again, just like the last one, I don't have any problem with this answer. Okay, but again, this guy's a constant, that guy's a constant, so we know constants are always similar terms, so we could add them together. And so we get natural log of absolute value of x squared plus 16 plus x plus some constant of integration, call it whatever you want. I'm just going to continue to call it c. Okay, and so we have what I would consider two acceptable forms. Okay, remember, it depends on who's in front of the class. Okay, you might have a professor that will say it has to be in this form. You might have a professor that says either form is fine. It's just a matter of what they want. Okay, guys, that'll do it for today. We've got one more situation we got to look at tomorrow, and you guys stay safe, and I miss all of you.